Welcome to the Explainer. So let's just jump right into it. Today, we're cracking the code on something that honestly sounds pretty intimidating at first, linear polynomials. But here's the secret. They are actually hidden in plain sight all around you. We're going to see how everyday objects, things like a simple box of pens or the wooden fence in your backyard, are actually the literal keys to understanding algebra. If you've ever found yourself asking how math actually translates into the real world, well, you are in the exact right place. We're going to take those real-world mysteries and turn them into solvable algebraic equations. Here's our quick roadmap for today. First, we'll meet the polynomials. Second, calculating real-world costs. Third, spotting linear patterns. Fourth, linear growth and decay. Fifth, a little exam prep and summary. And finally, number 6, a pop quiz and practice. All right, section 1. Let's officially meet the polynomials. Imagine you're walking into a stationery shop. You see a bunch of red boxes, and you know each one has exactly 4 pens inside. You also see some blue boxes, and each of those holds 5 pencils. Now, if you aren't sure exactly how many of these boxes you're going to end up buying, you can just use letters to stand in for those unknown quantities. We call those variables. So, let's let x be the number of red boxes and y be the number of blue boxes. That means the total number of pens you get is just 4 times x, or 4x. The total number of pencils is 5 times y, or 5y. And hey, what if the shopkeeper randomly throws in 3 extra loose pens totally for free? Your total haul is now perfectly represented by the algebraic expression 4x plus 5y plus 3. See, you literally just turned a quick shopping trip into algebra. Now, a really crucial step here is understanding the specific tools we're working with. Look at that shopping trip expression again, 4x plus 5y plus 3. It uses 2 completely different variables, x and y. But to make things easier for our journey today, we're going to simplify. We are going to focus entirely on expressions that have only one variable, things like x squared plus 1, or simply 4x. Narrowing our focus down to just a single variable really helps us isolate and understand some specific mathematical patterns. And honestly, this perfectly brings us to why we use the word linear. When we deal with one-variable polynomials, we have to look at the power, or the exponent, that's attached to that variable. The absolute highest power an expression has is called its degree. Notice those variables with the little 2's and 3's floating above them? Those are quadratic and cubic polynomials. They create curves and more complex shapes. But if you look at 3z plus 7, the variable z doesn't have a visible exponent at all. That just means its power, its degree, is simply 1. That right there is a linear polynomial. And they are incredibly special because, as we're going to see, they create perfectly straight, steady lines and extremely predictable patterns. Moving on to section 2, calculating real-world costs. Let's say you have this beautiful rectangular garden in your backyard. We'll call the length of it L and the width W. You've decided you want to put a sturdy wire fence along both lengths, a nice wooden fence along the widths, and you want to plant some special grass seeds across the entire area inside. How do you even begin to set a budget for that? Well, by turning that physical space directly into algebra. Let's break the whole thing down step by step. The wire fence is 100 rupees per meter, and you have 2 lengths to cover, so that's 2 times 100 times L, which gives us 200L. The wooden fence, that costs 80 rupees per meter across the 2 widths, so 2 times 80 times W gets us 160W. Now for the seeds, they cost 50 rupees per square meter. Since area is just length times width, that's 50 times L times W, or 50LW. Add all those distinct parts together, and your total landscaping cost is exactly 200L plus 160W plus 50LW. Boom! You just built a multivariable algebraic expression that calculates a real-world budget. Okay, so how does an expression actually become an equation? Think about this classic puzzle. The sum of 2 numbers is 64, and one of those numbers is exactly 10 more than the other. Let's make the smaller number x, which naturally makes the larger number x plus 10. Their sum is the expression x plus 10. Now set that equal to 64, and suddenly you have a solvable equation. Simplify it down to 2x plus 10 equals 64. Subtract the 10, divide by 2, and you find that x equals 27. So the smaller number is 27, and the larger one is 37. All right, section 3, spotting linear patterns. It really helps to think of a linear polynomial like a highly predictable factory machine. You feed some raw material into it, the machine processes it, and out pops a finished product. If our machine is programmed with a specific function, y equals 2x plus 3, and we input an x value of 4, well, the machine multiplies that 4 by 2 to get 8, adds 3, and perfectly outputs an 11. And here's the beauty of it. Every single time you put a 4 in there, you will get an 11 out. It's a completely reliable, rock-solid mathematical relationship. Let's look at this predictable machine out in the wild. Imagine a chess club that charges a flat 200 rupee joining fee plus 50 rupees for every individual match you play. Notice the pattern in what you're paying. One match is 250 rupees total, 2 matches is 300, 3 matches is 350. Are you seeing the pattern here? For every single match played, the total cost increases by exactly 50 rupees. That constant rate of change is the absolute hallmark of a linear pattern. So if you play M number of matches, your cost is always going to be 200 plus 50M. We can even spot this constant rate of change in basic geometric shapes. The perimeter of a square is just 4 times the length of one side, right? Or 4x. Now, if you take a square and you increase its sides by just half a centimeter, what happens to the total perimeter? It grows by exactly 2 centimeters. What if you increase the sides by another half centimeter? The perimeter grows by another 2 centimeters. It honestly doesn't matter how massive that square gets. That rate of change is totally locked in. It's perfectly linear. Which naturally brings us to section 4, linear growth and decay. So when that constant rate of change is going up, we call it linear growth. Picture yourself hopping into a taxi. The base fare just to get in is 100 rupees, and then it costs 60 rupees for every single kilometer driven. At 0 kilometers, you're at 100. Drive 1 kilometer, it's 160. 2 kilometers, 220. The cost is stepping up by exactly 60 rupees for every single kilometer traveled. Because the quantity is increasing by a fixed amount over equal intervals, that is the textbook definition of linear growth. But hey, what happens when things steadily go down instead? That is linear decay. Check out this timeline of a water tank evaporating during a hot summer. It starts out at 3 meters deep. After month 1, it's down to 2.5 meters. Month 2, it's at 2 meters. It is losing exactly 0.5 meters of water every single month because it's decreasing by a fixed, constant amount over equal intervals of time. It is a perfect example of linear decay. And you know what? This brilliant concept absolutely applies to the tech you use every day too. Say you buy a 600 rupee prepaid phone plan, and your telecom provider deducts exactly 15 rupees from your balance every single day you use it. Your phone balance is experiencing linear decay. It's just a steady, predictable countdown. Let's move to section 5, exam prep and a quick summary. Let's rapid fire lock in these golden rules so you've got a mental cheat sheet ready for your exams. First, algebraic expressions simply combine variables and numbers. Second, a polynomial is strictly linear if the highest power of its variable, its degree, is exactly 1, so no squared or cubed variables allowed. Third, a linear pattern will always feature a constant difference between its values. And finally, if that constant difference is adding up, you've got linear growth. If it's steadily subtracting, that's linear decay. Master these points and you've completely mastered the core concept. And finally, section 6. It's time for a pop quiz and some practice. All right, let's jump in. Question 1, what is the degree of 4z minus 3? Well, that variable z has an invisible power of 1, so the degree is definitely 1. Question 2, what's the coefficient of z in 4z cubed plus 5z squared minus 11? Notice there is no plain z term in there at all, which means its coefficient is simply 0. Question 3, find the constant in 9x cubed plus 5x squared minus 8x minus 10. Remember, the constant is just the number flying solo, and whatever you do, don't forget the sign. So the answer is negative 10. Moving to question 4, let's calculate some linear growth in nature. A plant starts out at 1.75 feet tall and grows 0.5 feet every single month. How tall is it after 7 months? You just multiply that 0.5 growth rate by 7, which gives you 3.5. Add that to the starting height of 1.75, and you find the plant is exactly 5.25 feet tall. And for question 5, let's look at linear decay. You buy a phone for 10,000 rupees, but it decreases in value by 800 rupees every year. What's it worth after 3 years? Well, 800 times 3 is 2,400. Take your starting 10,000, subtract that 2,400, and you are left with a final value of 7,600 rupees. You guys absolutely crushed that. So let's wrap this explainer up with one final challenge for you to tackle on your own. Imagine a village that starts off with 750 people, and exactly 50 new people move in every single year. Based on everything we've uncovered today about constant rates of change, what would the linear expression be for this scenario? And, more importantly, What will the exact population be after 6 years? I'm going to leave you to calculate that final growth on your own. Keep your eyes open for those linear patterns out in the wild, and once you figure out that population number, ask yourself, what else in your life is secretly just an algebraic equation waiting to be solved?